Okay, today we will continue about convolutions. I will give you a more formal definition of the convolutions. And oh, you don't see anything? So I will give you a more formal definitions of convolutions, and we'll try to see what kind of things are happening in the convolutions world. For the next week is the mid semester of the week of the semester, and I wonder if you are supposed to do the exam next week. Let me ask Yakup Hoca. Yakup Hoca, are you there? Are you? Let me invite him. Hocam dönemde haftaya dönem ortası ya, sınav yapıyor muyuz haftaya? 8. hafta. Tamam. Okay. Okay. So the exam will be not next week but the other week, midterm exam. So it will be on 16th of November. Okay, midterm exam. It will be during the class time. It will be closed book exam, face-to-face exam, and everybody has to come to class, and you will be responsible from all the topics that we have covered. So there will be some definition questions. What is this and this? And there will be some maybe some problems. If my network is this and this, and give me the output or that kind of stuff. So going over the slides and reading the material that you are given at the class material section should be enough to prepare for the midterm. So in 2 weeks you have your midterm exam. Okay, so let's talk about the convolutions again. Okay, the convolution networks, as we have seen last week, they are simple neural networks. Okay, instead of using general matrix multiplication, remember at each layer we have a input vector and we multiply with the matrix, and we output another vector and we pass it along. With the convolutions we don't do that. Instead we have convolution operation, and the convolution is not an invention of deep learning people. Okay, convolution has been known for a long time in the signal processing community. They use this operation a lot. And let's look at the formal definition of convolution. This is kind of a classical example of how to tell the convolution. Let's say you have a, let's say you are in a vehicle, a car for example, and this is your car. Okay, this is my drawing of a car. Okay, there is a wall like maybe 2 kilometers away. Okay, you are going towards this wall and you have a laser beam. You send laser beams to this wall and you receive the beam back, of course. And by measuring the time between your release of the beam and your reception time, you try to understand how far you are away from the wall. So if I draw a graph like this, okay, so this is your time, At time 0, you are 2,000 meters away from the wall, and you are moving towards the wall, and you keep sending this laser beam and receiving the reflection and measuring the time between. So you would have some, if you are using the constant speed, you would get something like this. It wouldn't be exactly perfect line because there is always this measurement noise, okay? It is either because of the signal generation or the reception or maybe some vibrations of the earth. I don't know. I mean, you don't get perfect line. You get a noisy kind of line like this. So what we like to do is, okay, this is xt, okay? Xt is your guess about how long you have, how far the wall is to you, and t and xt. We started from 2,000 meters, okay? So usually the standard thing here to try this convolution operation to smooth this line out, okay? I like to smooth this line so that it looks nicer and it is easy to use it in mathematical calculations. That's what we are going to do. For that, we are going to take, okay, a weighted average of it. Remember, xt is our function, a distance function. There will be a windowing function like this. Let's say this windowing function is around 0. It is like this. So around 0 it is high. Away from the 0 it gets close to 0 and becomes 0 somewhere. So st is our new result. So this is an integral from minus infinity to infinity actually. Okay. So this says that change to calculate the new st, okay? Okay, st, let's make st green. To calculate the new st for every point of t, okay, put t in here. So xt is related to xt, but you need to multiply that xt value with this w t minus a. So when a is t, this w is 0. So I am looking at this point. So I am multiplying with the highest numbers with xt. But when I am away from the value of t, then that number will be multiplied by a smaller number. It's in a way that, let's say my t is at this point, t is here. So I will be affected to calculate the st. I will be affected from this point a lot, and I will be affected from this point and this point, but the amount of effect will not be that high. If I do this, my st will look like maybe a more straight line than the blue curve. Okay, this is called the convolution operation. So the convolution operation, it looks expensive. So for every point of t, you have to run this integration over from minus infinity to infinity, and usually we show this using this asterisk sign or the multiplication sign or the star sign, whatever you call it. You say that this is my original signal, and this is my the window function or filter. Sometimes we call it filter. If I take the convolution of the filter with this image, with this input signal, as a function of t, I will get the new function s. It is smoothed version of the original x. Okay. So if I look at this, of course we are in a discrete world. We are not in a continuous world in the computer environment. Nothing is continuous in the computer environment if you have a digital computer. Okay. There are analog computers that work with the analog data, but we don't use them anymore. Digital computers are far better than the analog computers. So if I do this a convolution operation for all the points of t, then I would get a new discrete data. So x is our input. This is input. This omega is the kernel or the filter. Okay. Or the window. And the resulting thing is the feature map. Okay. So the type of ST is very similar to type of XT. ST and XT are similar. The only thing is that ST is a smoothed version of XT. This is called the convolution operation. I am sure many of you knew this before, this standard convolution operation. And we are going to keep using this. We will keep using this for the convolutional networks as we made an introduction last week. And it is easy to generalize this to more than one dimension, 2 dimensions. All you need to do is, of course, your input has to be 2-dimensional. Your kernel or your filter, your window has to be 2-dimensional. Okay? And instead of using integrals, of course, in a discrete world, we are using the summation operations, and that's it. So in this kind of case, of course, this is our input, and this will be our output. This is the kernel. Okay. In deep learning world, these kernels are learned. Okay, those are our parameters in the deep learning world. But in some other applications, those are not learned, those are handcrafted. Somebody manually designs them and fills in the numbers and says that, okay, this is my kernel. Okay? So, but in deep learning, we don't try to do that. We say that all of our convolutions or all of our convolution kernels will be learned by the training phase of the neural network models. Okay, I think last week I showed you this one. So in effect, this is, let's say, I have an image 3×4, and I have a kernel 2×2. If I do this convolution, I convolve with k. This is of course I, and this is k. These are the things that I am doing with the operation. So what I do is get this, okay, take these 4 pixels or 4 matrix elements, put on top of these 4 elements of the input I, and multiply the corresponding ones and add them together and put it in the new image. Okay, so this is A times W, B times X, E times Y, F times Z. Add them together. And do the same thing again. Take these 4 and put it in here. Okay. Do these multiplication and additions and put it back there in the final image. So if I convolve this image with this kernel, okay, if I convolve this image with this kernel, then I would get this result. Okay, good. So let's go back and let's look at some of the famous kernels actually. What did I say before? Previously, people used to design and calculate their kernels themselves. And here's one example. Sobel kernel. Okay. Somebody came up with this idea. They said that, okay, I have 2 kernels, GX kernel and GY kernel. Okay. And if we apply this kernel to this image, okay, resulting images, resulting data, resulting feature map would be this one and this one. Let me open that window. It is visible, right? You see it. Yeah. So let's see what we are doing actually. Can we explain this? We are going to apply this to an image like that, and just for the sake of simplicity, I am going to draw this image. It's not going to be very large image, okay? If my numbers are, for example, 100, 100, and 50, 100, 100, 60, 100, 100, and 70. So my image at the corner is like that. So what am I going to do? I am going to multiply this -1 with 100, 0 with 100 again, +1 with 50, okay? I will keep doing this. And if I do, you just calculate this, what is the final result? Tell me what the results will be. So it will be 50 and 80 and 30, 80, 80, and it is going to be 160, right? Is that correct? -160. Is that correct? So this result, so the resulting image will be at the corner -160, right? So keep doing this, I will get a new image. But it looks like I get a negative number. I get a negative number by just doing this multiplication and addition. And I like to show these kind of results as an image. Images are, as you know, their pixels start from 0, okay? Their pixels start from 0, and their maximum number could be 255, right? Between 0 and 255. This one is talking about 160. So just tell me, what would be the smallest number that I can get out of these multiplications and additions? So this is a regular image. All the pixels change from 0 to 255. This is my kernel. So what would be the smallest number and the largest number?
-400.
Minus what again?
-400.
400? Where did you? But I mean, you are assuming that the pixels could be at most 100. No, the pixels could be at most 255. Right? It would be at most 255. So if I have something like this, 255, 0, 0, 255, 0, 0, 255, 0, 0. What would this be? This would be 255 times 4, right? Minus 255 is 4. It is what? 1,000? Is it more than? Yeah. It's 250 times 4 is 1,020. Yeah. It is like minus 1,020, right? That would be the smallest. And largest would be just the opposite. Largest would be 1,020. So instead of producing an image, I am producing a matrix that contains numbers between -1,000 and plus 2,000. I don't like this because I cannot show it as an image. So what am I going to do? I would take this range and I would linearly map it between 0 to 255. Right? If I map it from 0 to 255, okay, and if I show it as an image, okay, for this one I would get one of these, and for this one I would get one of these. I don't know which one I would get for each one. Let's try to see, okay. So in this image, in this feature map, the final resulting feature map, okay, final resulting feature map, I have the numbers from 0 to 255, okay, from 0. 0 means that it is minus 1,020. 255 means that it is plus 1,020. So everything is squished between 0 to 255. Okay, so that means that 128 is the original 0, right? So 120 is like a gray. So these these areas that are that seems like the flat areas, that they correspond to flat areas of the image, because that doesn't, it look like this. Suppose I have all 50s here, 50, 50, 50. So what would be the result of the convolution operation on this window? What would be the result of the convolution operation? Doesn't matter if I apply this one or that one.
0.
It will be 0, right? But it is 0 in this range, but if I map it to this range, 0 to 255, it would be 128, right? So 128 represents flat windows. Okay, flat windows. Okay, so let's look at this image now. This image looks like it produces large values and some small values. Look at these values, okay? Look at this part. The upper part of this break line is all white. That means that those are large, and the lower parts are black, right? So upper parts are. So it looks like this kernel is kind of trying to detect changes in the vertical direction, right? In the vertical direction. So it is sensitive to vertical changes. It likes like this, okay? This one is trying to take the difference between the vertical lines. So it looks like this one is this one. So this is the result of GY. And this one is this one. This one is vertical lines. Okay, this one is sensitive to changes in the horizontal direction. If something changes horizontally, yeah. So I'm getting this. See the difference between this one and this one. So one of them is sensitive to changes in the vertical directions. The other one is, yeah. Okay. So like this. Maybe this one is better. Yeah. So one of them is sensitive to vertical changes in the vertical. It doesn't care anything about this, and this one doesn't care much about this one, but it cares about this one. So these are called kernels, Sobel kernels, just two of them. In 70s and 80s, people used to use these two kernels to run their computer vision or image processing applications. Okay, they didn't learn their parameters. This was already designed by the guy named Sobel. Okay, and then we have the Gaussian kernels. They are larger and they are parameterized actually. You don't design them by putting these numbers in. Okay, you calculate the numbers inside the kernel using this Gauss distribution. Just look at these numbers. In the center, it is highest. Okay, then I have this ring, then I have this ring, then I have this, not that ring. Let me try to do it in this ring, and finally I have so at the beginning I have 36, then 24, then 16, and it goes that way, right? So at the end I have 1. So it is symmetric. It is largest in the center, and if you add these numbers, it will add up to 256. I am normalizing it by 1. So or if you add up all of them, you will find 1.0. So when I apply this kernel to this image, this would be my final result. Well, let's notice this. Let's see something. This one doesn't have any negatives in it, and since the average of this kernel is 1.0, I don't have to normalize anything. This is the direct result. Apply that kernel to this image, and this is what I get. What do you see? What happened to my original image? What happened to my original image?
It's blurred, sir.
It is what?
It is blurred.
It is blurred, yes. It is softer, it is blurred, it lost detail. So that's the effect of the Gaussian, okay? Gaussian, so it is called Gaussian Blur. There are very nice features of this filter, Gaussian Blur. And nice thing about this Gauss is you can get this matrix, two-dimensional matrix, by doing the outer multiplication of these two vectors. For example, 1 times 1 is 1, 1 times 4 is 4, 6, 4, 1, and then, okay, and then 4 times 1 is 4, 16, 24, 16, and 4. You see that, right? So I can get all of these lines by just multiplying these two vectors using the outer multiplication, not inner multiplication, but outer multiplication. Okay, good. So it's like I am multiplying a matrix. This is like a matrix and this is like a matrix. Matrix to matrix multiplication. Okay, this is another famous kernel. Another famous kernel is not a single filter, but many filters. It is called Gabor filter bank. In the Gabor filter bank, okay, these are our kernels. They look like Gauss, but it is not in the center. It is the highest and the slow. It has some parameters. First, okay, it has this nice sine wave in it, right? And it is not single dimensional, it is two dimensional. I can change the direction of the sine wave like that, or where is my vertical sine wave? These are, yeah, okay, this one. So like that. That's one thing. The other thing is that I can change the frequency of sine wave, like this one, you see? This is very small. Compared to other one. The frequency is very high. Compared to this one, the frequency of this one is very high. I can change the orientation. I can change the frequency of it. And I can change the size of the envelope. Okay, these ones are small and these ones are large. So there are some parameters. And if I apply these kernels to the same image, this is what I get. Okay, I am applying the different kernels to the same image. This is what I get. Okay, so many kernels, I am applying them. It's like many kernels, many filters applied to the input image in the deep neural networks or deep convolutional networks. Okay, so as you see, some of the kernels are sensitive to, for example, eyes are detected. Some of them, like the lips, like the vertical structures, some of them respond to the chin area, etc. So each one is kind of trying to do something, okay? Okay, each one is trying to do something. In deep learning, our filters are trying to do the similar stuff, try to detect something for each kernel, but we don't know what those filters are. We did not design them. We don't force them to follow a model or anything like that, okay? They are automatically learned by the result of the training operation, okay? By trying to minimize the loss, we get the final kernels. Okay, so these are some of the kernel types that we knew so far. So before deep learning and the convolutional neural networks, people used to design these kind of kernels themselves and apply them. Now we don't do that, okay? We let the training operation come up with these numbers, okay? Instead of using a few kernels, like 1 or 2 or maybe 15, we are using at each level, we are using maybe 40, 50, 100 kernels, right? Remember, AlexNet, at each kernel, at each layer, it had at least 50 kernels, sometimes 128 kernels, okay? It is not possible to design those kind of stuff by hand. Okay, so the why we are using the convolution, there are some, remember when I first told you about the convolutions, what was our motivation? Without the convolution, there was a very serious problem. Remember that Einstein picture? Einstein picture, 200 by 200 picture. What was the
location of the features was the problem. Previous things were location dependent, but convolution removes the location.
No, not exactly. Before that, not even before that. And before the location problem, because we connected everybody with everybody, there is no problem of location there. So what was the problem? Running a fully connected layer at the first layer of the convolutions.
It was very big.
It was very big. Too many numbers of parameters, right? That was the problem. So with the convolutions, okay, we share parameters and our interactions are sparse. So both of them are very nice features, okay, to save number of parameters, to use this, to save space from the number of parameters, also the CPU time. And we are going to add this equivalent representation, and we are going to look at this applicability for varying size inputs and etc. This one is not that important. This one I will separate it, but the first three are very important. Sparse interaction simply means this, okay? This is fully connected network. I have 5 inputs and 5 nodes. Everybody is connected to everybody. This is sparse, okay? This one has 5 times 5, 25 connections. That's why 25 parameters. This one has 3 times 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. For some reason, 13 parameters. Okay. If we increase the number of nodes, this difference will be even larger. Okay. So sparse interactions instead of dense interactions are good for saving space for the parameters, small number of parameters. Okay. So that's the sparse interaction. Okay. We need to store fewer parameters, and then convolutions are kind of doing that. Convolutions are doing that. Some people say that, well, this one, all the nodes are connected to all the inputs, so that's something nice. But we can get the same effect adding one more layer. Okay, we can get the same effect adding one more layer. Instead of fully connecting everything to get, for example, this S3 knows about all of them. This S5 knows about all of them. But we can get the same effect adding one more layer. See, this G3 knows about all of them. So we can get this right. And then with the convolutions, we do the parameter sharing. We keep using the same parameters, 3 by 3 window, in all over the image. That means that we are saving some. We get to use the same image to train our 3 by 3 window in many places. So I don't need that much data to train my network. So that's the parameter sharing. That's the nice part of it. So this is one good example. I get this image out of this one. As you see, it is sensitive to horizontal changes like that, right? I get this image out of this one using only 2 numbers. That number is that kernel is just -1 plus 1. That's it. Just 2 numbers will give me this image. So this one is sensitive to horizontal changes. That's it. So instead of, if I remember, let's imagine I am trying to do the same thing with a fully connected network. Fully connected network was going to have 200 times 200 times 200 to the power 4, so 4 billion parameters. Now I'm doing the same thing with just 2 parameters, and it is purposeful. Okay, of course we never do this kind of stuff with the neural networks, but just trying to show you what kind of advantages we are having. Okay, then the other thing is equivalency. Equivalency, although the name is kind of fancy, kind of complicated, it's not actually. It says this: it doesn't matter. Let's say I have two functions. Okay. Okay. It doesn't matter if I do this or that. Okay. Fg of x or gf of x. So this is kind of in a way doing this. Convolution is equivalent to translation. It doesn't matter if you apply your convolution, then you translate your image left, right, up, down, or if you translate your image left, right, up, down, then apply convolution. Doesn't matter. It is the same thing. So it is equivalent against the translation convolution. It's a very nice feature. Why? Because I am not position dependent if I am doing the convolution. In any place of the image, if I see the feature that I like, my convolution filter will respond to that feature. Okay, so convolution is equivalent to translation. Okay, so that's another thing. Unfortunately, convolution is not equivalent to rotation. When you rotate an image, I will not get the same effect from my convolution filters. Okay, I will not get the same effect for my convolution filters, but we have some nice solutions for that problem. For the translation left, right, up, down movements, convolution produces almost the same result. But if I rotate the original image left, right, convolution will fail. I mean, I will not get the same response from my filters. We have to do something else. Okay. Usually we use pooling, as I said last time. Usually we use pooling with the convolution. Okay. A typical layer of a convolution network has 3 stages. This is what we do. Okay. I apply the convolution. After the convolution, I have my detector stage. That is, I apply the ReLU operation or the sigmoid or the hyperbolic tangent, doesn't matter, non-linearity, then I do the pooling. Usually our poolings are max pooling or the average pooling or something similar. The most commonly used one is the max pooling. For example, here I am just choosing for this one, take the maximum of these 3 here, take the maximum of these 3 here, okay, and take the maximum of these 3 here. Okay, so this is the pooling operation. Max pooling is the more popular one, and with the convolution after the non-linearity application, we apply the pooling. That's kind of the common way of building convolutional networks. We talk about the translation invariancy. Okay, I will skip these. Remember what I said about convolution is not equivalent under the rotation. So what are we going to do? This is what we are going to do. We will have different filters that are sensitive to this orientation of images, this orientation of images, and this orientation of images. Okay. So in this case, if my input is rotated like that, this one will respond. If my original is rotated like that, okay, this one will respond. And if I pull these three filter results together, I will have a 5 detector here, right? Doesn't matter if it is anywhere on the image, I can do that, or doesn't matter if it is rotated left or right. Okay, so that's how I solve this problem of convolution is not equivalent to rotation. Also, the convolution is not equivalent to scale. If I have a large 5 or small 5, I should get the same detection 5, right? So it will be similar to this solution. There are some filters, they are sensitive to the small values, and there are some filters that are sensitive to the large pictures. Okay, any questions so far? From the online audience or from the class? How many people do we have? We have 9 people right now. There are 4 people here. Okay, not bad. For those of you who came late, let me... November 16th, we are going to have our midterm exam in class, face to face. Okay, not next week, but the other week. So I made some explanation about the midterm exam, and if you didn't hear that, just watch the video. Video will be available after the lecture. Okay. So is anybody presenting today? Do we have anybody presenting today? Let me see if I can find it from the paper presentation. I think we had 1 or 2 people maybe. So today is November 2nd. No, nobody is. Either somebody has raised their names. Okay, so there is no presentation today. But next week, okay, we have Bayesian learning-based adaptive control. Good. So another control paper is coming, and Başak is going to talk about deep learning for symbolic mathematics. Are you guys are ready? Başak and Fıratcan, are you guys ready? Or are you going to be ready next week? But it looks like next week we will have our midterm. So we are going to push you 1 more week.
No.
Oh, no. Sorry. Okay, so I am going to reserve it. This place, and I will take it out, or I will just do it like that. So nobody write their names here. And in fact, I can do maybe merge them together. Can I merge them? Yes. Yeah. I don't know what I can do with the merging. Anyway, I was waiting for you to ask me a question, but everybody's watching me instead of asking a question. Okay. Does anybody see where it merges? It should be somewhere around here. Is it under? No. Yeah, okay. It is birleştir ve ortala. Yeah, good. So midterm exam here. And let's make this a little bit larger. So I am done. Do you have any questions? Okay, so it is time to give, let's take some 10 minutes of break. After the break, we will come back and we will continue. So it's break time. During the breaks, I think I will stop this record. Or maybe did I bring my? I'm sorry, I didn't bring my charger. I have 64%. Okay, keep it. How come I cannot make this other than there is no battery save option? Anyway, I hope that would be, no, I am going to stop this.